Hi everyone, and thank you for watching this presentation. At Utrecht University, my colleagues and I have developed a reference method for developing action recognition classifiers, which I will discuss in this video. First, let me introduce myself. My name is Sabine Molenaar, and I have a background in information science and business informatics. My research interests include dialogue summarization and automated reporting in healthcare, and this research was executed in the context of the Care to Report research program. I want to start by describing the problem. Action recognition is concerned with the classification problem of labeling videos containing human motions with action classes. Actions can be described in many different ways using many different words, which are sometimes considered to be synonymous. To help define the term action, we use the following action taxonomy. Action primitives are atomic entities that comprise an action. Actions are a set of action primitives needed to perform an action. An activity is a collection of actions that describe a larger event. As an example, tennis is an activity that includes actions such as returning a ball, which is comprised of action primitives such as a forehand. In this research, we are only concerned with actions. There are some practical challenges when adopting action recognition. First and foremost, no systematic method for developing classifiers for domain action recognition exists. And secondly, machine learning literature often assumes the reader has some existing knowledge or experience. A method is often implicit. For example, it is explained how an algorithm can be implemented. And finally, domain understanding is often assumed and only introduced when a case study or experiment is described. I hear you ask, when literature does not describe a method, why is there a need for one? Well, in action recognition, multiple people can be present in an image or video, which leads to a risk of occlusion, meaning that people are blocking or obscuring each other. There's also a need to distinguish different subjects present in the data. Secondly, the field suffers from a lack of sufficiently large datasets that can be used in different contexts. These challenges and risks need to be addressed when developing an action recognition classifier in order to ensure that it performs well. To our knowledge, no systematic method exists for developing, training, and validating such classifiers. Our proposed solution is a reference method for the development of classifiers for recognizing actions and interactions in a domain, which we refer to as the DARC-method. This reference method includes a step-by-step process for the development of action recognition classifiers, a sub-process that describes the creation of suitable datasets, links to state-of-the-art techniques and literature, and the use of consistent terminology. The DARC method is meant for use by people with limited or no experience in machine learning. In our research, we have used the assembly-based method engineering approach, since many techniques, methods, and processes are already described in literature. The assembly-based approach consists of three main activities. The first is specifying requirements for the method. The second, selecting method chunks that will be used to create the method. And finally, assembling these chunks. We have formulated the following requirements for our reference method. First, the method should provide guidance to practitioners in information systems, so those with little to no experience with machine learning, rather than machine learning experts. Second, it should be tailored to action recognition classifiers. And lastly, the method should describe the development of a classifier for a specific domain from start to finish, but the method itself should be domain independent so that it can be applied in any context. Since we use the assembly-based approach, we have selected a starting point in existing literature from which to create the method. But since no systematic approach for action recognition could be found, we start from data science frameworks instead. We have compared three frameworks: the Common Task Framework, the Knowledge Discovery in Databases process, and the Cross-Industry Standard process for data mining. In the end, we selected CRISP-DM as a starting point, since it is designed for projects with large amounts of data, aimed at achieving business-related objectives, and covers the process from problem investigation to deployment. The assembled method is quite extensive and cannot be described in detail in this video, so for the sake of brevity, I will describe some of the main activities. First, in the domain understanding phase, domain action should be extracted, for example using literature or guidelines from the domain in question. Then, since the practitioner may not be an expert in this domain professionals should be asked to discuss the extracted actions to ensure they accurately represent the real-world situation. The dataset creation phase is optional because if a suitable dataset is available, this phase is not required and can be skipped. The extracted actions should be combined into sequences, since in some domains multiple actions are performed in succession. Then, variation in the dataset needs to be planned. We call the set of potential variation points variation heuristics. Some examples are hairstyles and clothing. In addition, if multiple people are present in the videos, they need to be divided over the different roles to ensure the classifier will be able to distinguish the roles and not the specific persons. After this has been done, the videos can be recorded according to the plan. The third phase is concerned with preparing the dataset. The recordings need to be edited, for instance to ensure they all have the same resolutions and frame rate. And then the recordings need to be cut into sessions. During recording, it may be easier to film multiple actions and sequences in a row, but this does not represent the real-life situation. All the sessions need to be annotated, which means that the videos are given the correct labels to describe what is happening in each video. To improve the quality of the annotation, multiple people can be asked to annotate. The differences in annotation can then be discussed and changed if necessary. At the start of the classifier modeling phase, a learning method for the classifier needs to be selected. The appropriate learning method is determined by elements such as the amount of data available. Once a method has been selected, feature sets need to be created or extracted in order to recognize the various actions. In addition, one or multiple classifiers need to be selected for the classification task. Many classification methods exist, such as random forest and k-nearest neighbor, but not every classifier is appropriate for every classification task or dataset. The choice may also be influenced by the available time and computing power. In the experimental protocol, the dataset is divided into training, validation, and test sets, although a k-fold cross-validation may also be used. Then, the classifier can be trained and validated using either k-fold cross-validation or separate training and validation sets according to the experimental protocol. The classifier is trained and validated using several parameter sets. The parameter set that yields the best performance can then be selected for testing the classifier. If the prediction accuracy is unacceptable after validations, there are 4 options. First, you can retrain the classifier using k-fold cross-validation. Second, different feature sets can be created or a different classifier can be selected. Third, the size of the dataset may be increased by editing or augmenting the recordings or creating synthetic data. And finally, additional data can be created from scratch. When the classifier is sufficiently accurate, it can be used in its intended domain in the deployment phase. The classifier may be used in a context system, so a system that is already in use in the domain. Finally, end users of the classifier may want or need to provide feedback on its performance. For instance, if users notice that one action is often recognized as another, additional data and training might be desirable. We have developed an action recognition classifier for a specific domain during a case study. General practitioners experience a high workload because they spend much of their time on administrative work. Identifying the actions they perform during a consultation, for example during physical examinations, can reduce the reporting time since they do not have to describe what they have examined. Therefore, our domain is concerned with general practice consultations in the Netherlands. We have included actions that are frequently performed by general practitioners in the dataset, but we have excluded actions that require subjects in the videos to undress for the sake of their privacy. Since we are not medically trained, we extracted actions from available clinical guidelines. The sequences of these actions were then determined with the help of medical professionals. We use variation heuristics to include variation in the videos. In the Netherlands, for example, general practitioners do not wear white coats, so we use different clothes in the videos. We also included both men and women in the videos. In total, over 400 videos were recorded. We used multiple angles to record the videos to avoid the risk of one subject blocking the other from view. Over 70% of the videos contain single actions or no actions, and the rest contain sequences of multiple actions. We distinguish 4 labels for each annotation, which are domain independent. They are region of interest, touch, posture of the subject, and the domain action that is being performed. For general practice consultations, we identify domain-dependent labels. For the region of interest, for instance, we included the labels arm, chest, upper back, and abdomen. It is important to include data that shows no actions as well, because in the real-life situations, actions are not being performed continuously, so the classifier should be able to recognize when something of interest happens. We have used the OpenPose system to generate key points and skeletal representations for videos, since it can recognize multiple persons and is publicly available. We found that using segments of videos, as opposed to single frames, was better for distinguishing between similar actions. For example, during palpation of the abdomen, both hands are pressed on the abdomen, while during percussion, one hand is not released from the abdomen while the other is. Therefore, percussion is easily confused with palpation, but in segments is more easily distinguishable. The prediction accuracy of recognizing medical actions was 75.6%. The accuracies of the other annotations, posture of patient, touch, and region of interest, are 99.6%, 91%, and 19.8% respectively. An example of how the videos were annotated is shown here. The region of interest is the upper back. The general practitioner is touching the patient is sitting upright, and the action being performed is auscultation of the lungs. To end the presentation, I would like to share some limitations, future research directions, and conclusions in the context of this research. To start off with the limitations, the method was applied to a single case and to one particular domain, which is general practice. It is possible that modifications are required when applying the method to other domains. We were also unable to test the deployment phase as of yet, and there is a chance that others less familiar with the method or domain may find its use more challenging than we did. However, the method is based on existing and validated techniques, which should improve its external validity. In the near future, we plan on conducting a controlled experiment with students with little to no machine learning expertise. The students will be given an action recognition assignment. The experimental group will make use of the DARC method throughout their work, while the control group will work without it. We can then assess the effectiveness of the method based on the efficiency of the students, the number of errors we detect in their work, and the quality of the resulting classifier. Also, we intend to apply the method to different domains and datasets. And finally, we will test the deployment phase by deploying the developed classifier in a real-world context. To conclude, the method provides guidance to users through a stepwise process, includes relations to relevant literature in the field, and makes use of consistent terminology. Also, it is tailored specifically to action recognition, but other than that remains domain independent. This is in line with the requirements. The first requirement is that it should provide guidance to non-expert users. The second is that it should be created with action recognition classifiers in mind. And finally, the method should be domain independent and cover the development process from start to finish. Thank you for listening, and if I've piqued your interest, I would like to invite you to read the full paper.